but the Chilean registered the name first. So okay.
I think you have a mission on the Lagrangian on your T-shirt. You're missing the dark matter.
Okay, so it's a pleasure to be here. I want to thank the organizers, and especially for giving me the opportunity of talking in this workshop. And today, I'm going to talk about dark matter and vector fields in non-trivial representations of SU2. I suppose. Okay. And the content of my talk is this one. First, I'm going to explain why I want to consider vector fields. Then I'm going to describe a very simple model with a vector resonance in the dark sector. And then I'm going to describe some models with the spin 1 vector as the dark matter candidate. And after that, I'm going to state my conclusions. Why consider vector fields? Well, vector fields are wild animals that have to be tamed. And usually they are tamed introducing gauge symmetries. Here, you can, oh, I know it's off. Okay, that's okay. Here you can see Alexander the Great taming his horse Bucephalus. This is not the classical image. And usually we need gauge symmetries to construct consistent theory with massive vectors fields. However, in nature we know examples of massive vectors which play different roles. For instance, in the hadronic sector, we have the rho meson, which can be seen as an emergent gauge boson in the spirit of the hidden local symmetry. But the A1 axial vector behaves like a matter field in the sense that it transforms homogeneously under the hidden local symmetry. And of course, this example comes from a non-fundamental sector. But anyway, nothing prevents its realization in the dark sector of nature. So I'm going to describe a very simple model which includes a vector resonance in the dark sector. The model is a simple extension of the inert doublet model. The extension is done by increasing the symmetry of the model. We increase the gauge symmetry to SU2 cross SU2 cross U1. And this symmetry is broken down to the standard model SU2 through the wave of this link field. We put each doublet in each SU2. I mean, one doublet transform under SU21, and the inert doublet transforms under the additional SU2. We introduce an additional hypothesis. We assume that the new sector, the dark sector, is strongly coupled. I mean, the typical coupling constant of SU2 is much bigger than the coupling constant of SU21. So this kind of scenario can reflect, for instance, the case of a strongly interacting sector in the dark sector, and this doublet and the gauge boson here can be considered as a composite state. Oh, yes, yes. Here it is a bidoublet, but we really consider this like a nonlinear sigma model matrix. It's a Nambu-Goldstone matrix. So the spectrum of the model is the same you find in the inert doublet model, with an additional triplet of vectors, which we call rho. And we focus on this mass range for the new triplet, vector triplet. The parameters are the same of the inner doublet model, with the addition of this A parameter, which is the ratio of the new scale of symmetry breaking and the standard symmetry breaking scale. And the other new parameter is the mass of the vector triplet.
One question, Alfonso.
Oh, yes.
So, the SU2 of our usual standard model is a diagonal one of those breaks, right?
Yes.
I have a doublet under that. Where are those other X's? Where do those, those in the next slide, where are your H1 and H2? What field are they?
Oh, okay, okay. So, this one is the inert doublet. So, H1, H2, and the chart 1 belongs to phi 2. And this is the standard model like doublet.
So the standard model doublet is charged for SU1, not the diagonal.
Yes, yes, yes. Yes. And the capital H is the standard model like Higgs. Okay. Now, we compute the Rayleigh densities in this model, and for the low mass range, okay, our candidate for dark matter is H1. H1 is our candidate for dark matter, as in the inner doublet model.
Are you permitting somehow crosstalk between H1 and H2? Because through sigma, that you should be able to write down terms that mix them. Are you permitting those?
Okay. There are terms, there are interaction terms between phi 1 and phi 2, but they are not mass mixing terms, because phi 2 is odd under a Z2 symmetry, like in the inner doublet model. So there is not mixing. There is not mixing. Okay. So in the low mass regime, the results are identical to the inner doublet model, but in the large dark matter mass regime, there is a big change. Usually, in the inner doublet model, in this region, you can saturate the Rayleigh density, but now the Rayleigh density goes down because you have new annihilation channels. This is a resonant annihilation mediated by the new vector triplet. And here you have annihilation of dark matter into the new vectors. So here the Rayleigh density is lower than expected in the inner doublet model. This is the same, but in the case of non-degeneracy of.
Do you have new variants or no?
No. Only the only modification was to include a new vector, a new vector triplet. Okay, this is another, two other plots for the Rayleigh density in terms of the mass of the dark matter candidate and the mass of the vector resonance. And you can see here the dip in the Rayleigh density caused by the resonant annihilation mediated by the vector triplet. This is the parameter space after considering all the experimental constraints and imposing that we have to saturate the Rayleigh density. So we can see that only masses of the dark matter below 1/2 of the matter of the resonance survive. The new resonance can be searched at colliders. Here I showed the predictions for the LHC. You can see that the cross section are quite small, but the new vector produces produce an enhancement of the cross section of in the case of the monoset production compared to the prediction of the original inert doublet model, especially in the region where the vector resonance is light. Light, I mean relatively light.
So it's black just because in that model there's no resonant enhancement in the cross section, whereas you have that.
Exactly. This is due to the resonance. This is completely expected. Huh? Well, this is a similar plot for other channel of monoset production. We also explored the possibility of testing the model at click in the high energy regime because the new resonance, the new vector can be produced as a resonance in this channel, in the dimuon spectrum. We considered, in this calculation, we considered the case where the scalar are heavier than 1/2 of the new vector resonance mass. And we consider also the smearing of the momenta, so our resonance are quite broad.
Alfonso, one question. This resonance is related to which symmetry? Or just vector particle? Add vector particle.
I add the vectors like a new gauge bosons, the gauge bosons of the new symmetry, because I extended the symmetry of the inert.
But you have two doublets, one inert one and a model one.
Yes.
But, this new symmetry is related with this vector boson related to symmetry associated with neither SU2, one of the.
No. The resonance are the gauge bosons are mainly the gauge bosons of the second SU2.
Second SU2. But this means that this SU2 inert doublet is not weak SU2. So
No.
Is it different?
No, exactly. The new resonance is mainly the gauge boson of this SU2.
So you also have a W prime.
Exactly.
And the Z prime.
Exactly, of course. This is a triplet. This is a triplet.
So this is a completely different model in comparison to IDM. Even if I take vector resonance apart, because IDM usually is both doublets are doublets of SU2.
Exactly.
Now we have completely new inert doublet.
Yes.
Related to new SU2.
Exactly. But the gauge bosons of this group couples to the standard model fermions, for instance, only through mixing with the gauge boson of this group. And the mixing is proportional to G1 over G2. So it's small. It's small. So the dark sector is weakly coupled to the standard model sector, I mean, to the visible sector.
Some sense of kind of technical, well,
Yes. This is it's very similar to the Rho meson and the pion in the hadronic sector. It's almost a copy of that. So at click, here I'm showing the cross section of the signal. I mean by signal the cross section, the resonant cross section in this channel at click. We compute for different value of A. I recall you that A is the ratio of the two symmetry breaking scales. And here we show the background cross section. We can observe that the signal is comparable to the background. So the signal to background ratio is of the order of 1, and in principle the resonance can be discovered at click.
Is this also the case with
Yes. Yes, it can decay to W and C also.
Shouldn't that be a briefing case, since then that's enhanced longitudinal polarization? Expect sort of an analogy with
Yes, we didn't consider this channel. We prefer to consider the decay in mu because of, I think, the background here is under control. It's more under control. That was my motivation. We explore also the possibility of detecting a monojet signal at click. Here, the situation is more difficult because the background is huge compared with the signal. The only hope is to put CAT, to introduce CAT in the invisible invariant mass. I don't know if experimentalists can do that, but it's the only possibility to obtain a good signal to background ratio. Okay, but more interesting is to consider the case of vector dark matter. So, in literature, you can find a lot of possibilities for vector dark matter. For instance, you can consider Kaluza-Klein photons. I mean the Kaluza-Klein resonance of the photon. Little Higgs also, with T parity, can propose a heavy photon like a dark matter candidate. Or you can simply consider an abelian C prime with C2 symmetry. And a very interesting possibility is that dark matter is the vector part of a propagating torsion, which was proposed by Sasha Belyaev and Ilan Shapiro recently. A very interesting possibility. But in this work, I want to consider vector fields in non-trivial representation of SU2 as a possible dark matter candidate. Our first model consider isotriplet. I mean a triplet of SU2. The basic idea appeared when I realized some years ago that you can couple a gauge boson to a massive vector boson in this particular way, with this particular Lagrangian, with known triplet, with no trilinear vertex for the massive vector, so that the Lagrangian is invariant and under a C2 symmetry of under which the vector boson is odd. And another important feature is that there is only one coupling constant, which is the gauge one. It happens to be that this Lagrangian defines a theory which is consistent with unitarity, at least at 3 level. I'm not sure about quantum correction, but at least at 3 level, it is consistent with unitarity, and this is quite interesting. Another feature is that with a simple rotation, the Lagrangian can be written in this particular form, where A1 and A2 transform like a gauge bosons, like connections, under the same group, under the same SUN group. The basic idea is that the difference of two connections is a tensor. So this mass term is invariant, is gauge invariant. In this form, we have also only one coupling constant. So the Lagrangian features a sort of T parity. From the theoretical point of view, this is interesting because this Lagrangian is the Yang-Mills analog of big gravity. Big gravity, you have an action with two metrics which are mixed somehow. So this is the same spirit. You have two connections, and they are mixed by this mass term. So from the theoretical point of view, I think this is it's interesting. Yes.
So you have U1, and that's one is for the U1 level, right? The U1.
Exactly.
One is for U2, and when you say gauge invariant, this is after you break the symmetry and you get the SUL.
Oh, okay. Well, this is a different model from the one I explained first. This is not anymore the inner doublet model plus resonance.
So the SU2 is the same for 1 and 2. Then
Yes, here the SUN is, there is only one group SUN. Of course, you can see this theory like a theory based on this group broken down to the diagonal group with the mass of the Higgs bosons very, very large. So in this limit, you recover exactly this Lagrangian. But anyway, what is interesting is the consistency with unitarity, at least at 3 level. That's my main point. So the idea was to couple this Lagrangian motivated by theoretical reasons, to couple this Lagrangian to the standard model. So this is the result. Here you have the Lagrangian of the standard model, and this is the Lagrangian for the vector. Now because of the standard model included a scalar, the Higgs doublet, I have to add this term, which was absent in my original construction. So here, in this model, A is the coupling constant which control the coupling of the Higgs to the new vector. It's tempting to put this A equal to 0, but it would be generated at loop level, so we have to put here. Okay, this model is a really minimal extension of the standard model. We have only two free parameters, this A coupling constant and the mass of the vector. We checked unitarity, and unfortunately, we have problems with unitarity again because of two things, two reasons. The first one is the coupling with the Higgs, and the other one is that the gauge symmetry of the standard model is spontaneously broken. Indeed, when we compute the scale of unitarity breaking, you can see that it depends on the A parameter and the mass of the W. If you have A equal to 0 and the mass of the W equal to 0, that means the symmetry is exact, then the scale of the unitarity violation is infinity. Yes?
Which process is violating unitarity? Is it de-scattering or is it involved in electroneutral?
Okay. Originally, we checked this channel, and not in the standard model, but in the original general construction was the scattering of the gauge bosons producing the longitudinal vectors of the massive one. In the original case, when the symmetry is exact, the amplitude for this process is exactly 0, vanished completely at 3 level. And this one, in this case, the amplitude goes like a constant plus orders, term of the order of mv over s squared. So
How come DL
just because there is no trilineal coupling, and all the couplings constant. I mean, there is only one coupling constant, which is the gauge one. So, indeed, this is a very interesting feature because if you try to quantize gravity, for instance, the trilineal graviton vertex is problematic and introduce a unitarity violation. And the same thing or a similar thing happens in this model. So it's quite interesting from the theoretical point of view.
There's typically logarithmic terms that arise from integrals over phase space. And these logarithmic terms, even if you cancel the E squared growth, eventually become important.
Yeah. I didn't find any problem of this kind in this model. I mean, when I made I could compute the terms.
We play the game like this. You can solve unitarity, canceling things, canceling E squared growth, but there's always the log terms that say eventually you need to face up with the facts.
Yeah, maybe I failed to identify the log terms. Maybe when I made the expansion for large energies, for high energies. Maybe there I lost the identification of the logs. But anyway, the result is this one. That's what I found.
But you calculated the cross section or amplitude maybe?
The amplitude.
Yeah, and you're talking about the log term from actually cross section from safety. Yeah, I see. Maybe
Yes, I compute the amplitude. Okay, I'm late. We coupled the vector to the standard model, and of course, I have to say, because of the C2 symmetry of the model, the lightest component of the triplet, of vector triplet, is a good candidate for dark matter. It happens to be the neutral one.
Just out of my own understanding, those traces are over the ST2 of the standard model.
Yes. Yes.
So you are.
Yes. So we compute the unitarity violation scale in terms of the free parameters of the model. And we found that for masses of the vector large enough and A small enough, the scale of a unitarity violation can be as big as 10 to the 5 TeV. So from the phenomenological point of view, we are safe. The splitting of the charged and neutral component is produced by radiative correction, and it's very small. That implies that the charged components are long-lived, but the path, I mean, they can travel only about 2 centimeters before decaying, and this is not big enough to be detected as missing tracks in atoms, for instance. So it's not detectable. The relevant coupling for direct detection is this one through the Higgs, and this coupling depends on the A parameter, which is small, so we are safe. And with this model, we can saturate the relic density easily for masses of the vector large enough. We are safe, and with respect to direct detection, this black line represents the point which saturates the relic density, which is phenomenologically interesting, and this gray area is excluded by xenon 1T, but we are in the safe region. This is, we are also safe with respect to the Higgs going into 2-photon limits. And, well, after all the experimental constraints are imposed, and imposing the saturation of the relic density, this is the parameter space which survives. So the model is viable. We are also safe from the point of view, or almost safe from the point of view of indirect detection, depending on the assumption on the distribution of dark matter in the center of the galaxy. And this is the most important plot. Here, you can see the effective cross-section in the production of the charged component of the triplet and the sensitivity of the LHC and the feature circular collider. And we can see that a 100 TeV collider can completely exclude the model or discover the model. That's the message we want to put. We need a 100 TeV collider. We also studied the possibility of introducing vectors in the fundamental representation. This is the Lagrangian in this case. This Lagrangian have these terms which are not invariant under C2, but if you put this coupling constant to 0, an accidental C2 symmetry appears, and which protect the Lagrangian. Here the vector is a doublet, of course, and we assume that this component is the dark matter. We compute the relic density, blah, 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 blah. Time is running. Time is running.
You should finish your first talk now and then.
Exactly, that you'll have the discussion. And after imposing all the experimental constraint, we find that the model survive. We have a non-zero parameter space surviving, and we can saturate the relic density when the two neutral components of the vector field are quasi-degenerate. And well, this is the red point represent the region of saturation of the relic density. So I come to my conclusions. Vector fields can play crucial roles in the dark sector. We build extension of the standard model incorporating new vectors as matter fields in SU2. And the models contain natural dark matter candidates. In both models, the last two, a new C2 symmetry appears motivated by the theory, especially in the model with a triplet. The models are consistent with collider and cosmological data. And the vector in the fundamental representation is interesting, but is more challenged from the point of view of data. And also, the unitarity constraints are stronger. The model with an isotriplet seems to be more robust in that sense, and the scale of unitarity violation can be very, very, very large. So, and finally, the models can be complete ruled out or discovered at a 100 TeV collider. And as in Chile, in my country, there are protests and demonstrations these days. I want to add, and I demand a 1 TeV collider now. Okay, thank you very much.
Questions? I have one. So could you go back to slide 38? 38. So at some point the numbers are missed.
Yes.
Oh yeah, so that one. Could you explain how can you increase the annihilation cross-section, increasing the mass of the mediator? How can we increase the mass and increase the cross-section at the same time? So I was expecting it should be the other way around, no? Why the sigma V is increasing with the mass of this guy?
Oh, yes.
Because we just expect this to be in the propagator, so it should just decrease, right?
Yes. Yes. Let me see. I'm not so sure. The main process for indirect detection. The main process is V0, V plus, for instance, W, and W. And you're right, you have the propagator there.
But why? Okay, the bigger mass, the bigger phase space, and then double, right? What's the problem? Is cross section of the Middle East, right?
Right.
What is
Exactly. The problem is that
you agree?
you have you're increasing this mass, but you are also increasing
Yeah, that's the
this
point.
mass.
So these masses are not that
What-
very different.
Yeah, but you cannot increase space.
Yeah.
Yes.
So the cross section of the space.
Okay, but you can think about it. So there's another one that I had. So,
Sorry?
but then I would expect a peak, right?
No, not explicitly. No.
So I thought that it was a Sommerfeld effect. So I would expect a peak and then somewhere like a plateau or something. Yeah, might be.
Yeah, but no, unitarity is not the problem here. I mean, the unitarity violation is under control.
But still, maybe the mass and the longitudinal components, they are related. And, well, I need to check the cross section is calculated correctly. The question is, we need to find the interpretation.
Well, it's not just easy to catch by eye. So could you go back a few slides for the direct detection one? I think it's 35, 36.
I think I know the answer because the vertex is proportional to momentum, right? The bigger mass, the bigger momentum is going to double. The bigger the vertex is proportional to momentum of the incoming particle. The bigger mass, the bigger momentum is going to double. The more the factor.
Yeah, but then that would be the case for every single model.
Not for every single model. For the model where the vertex is proportional to the momentum involving vector, it will be the case.
Yeah. Anyway, so I think it's the 35. Yeah. No, 34. Yeah, this one. So why you have this like sort of resonance, whatever, for the spin independent scattering?
Ah, okay.
Like at 200 GV, 300 GV-ish? Yeah, 150 or something?
Okay. This is the mass of the.
Of V. So it's the same thing as we.
Yeah. This is the mass of the V, and this is the. I think this is the mass of the Higgs, right?
Yeah, but it would not induce like a resonance because it's scattering. So the momentum for direct detection is much, like way below any resonance for the Higgs.
Yes. Yes.
So the question why this big?
Yeah. Because for direct detection, we expect the momentum transfer is MEV, so we don't expect any resonance at like hundreds of GV.
We discussed this actually.
Okay. Anyway.
Okay. Sorry.
Any further questions? No.
Yeah.
Yeah.
Just a question. In the left-right symmetry, the people usually assume that the two coupling constants are the same. How well motivated is this assumption?
Oh.
Okay. I recall the answer on your question. Sorry. So the point is that the point is that when you're close to the Higgs mass resonance, your relic density drops a lot, right? And this is rescaled sigma. This is rescaled sigma. Yeah.
Oh, yes.
So it's due to reduction of the relic density.
Oh.
Yeah, the sigma is rescaled sigma. The spin independent scattering is rescaled yeah. That's that's the effect of the rescaling on the relic density.
Yes, you're right.
Sorry, it was a long time.
No, thank you, Sasha.
Okay. So regarding Diego's questions.
So originally, my original question was how to construct a consistent theory containing the gauge boson and the massive vector field. I think make the chromoelectrodynamics of a vector field. And I proposed the most general Lagrangian with terms up to dimension 4. This is the most general one you can construct. And then I compute the amplitude for these processes. This is the example of the first terms for the amplitude of this process. And I realized that with this wise election of parameters, you can obtain, you can cancel out the offending terms, the terms growing with the energy. Indeed, this election of values for the parameters cancel out the whole amplitude for this process, and this one also becomes in agreement with unitarity. So that was the reason to introduce only one coupling constant.
Can you check the inelastic terms, so the scattering to Higgs's?
Oh, this is in the original model without Higgs, without with an exact symmetry. When I coupled to the standard model, I checked unitarity. I did again the calculation and introduced the Higgs, of course, and that's how we find the unitarity violation in the model and compute the scale. Okay.
Further questions? So let's thank the speaker again. And we go for a coffee break.